So today we are going to talk about parametric equations. Okay? So parametric equations, basically we have two functions in terms of a third variable describing a curve. Okay? So it says f and g are continuous functions of t. And the set of ordered pairs f of t, g of t is our curve, okay? So what's going to happen, you are going to be given two equations, x equals and y equals, and they're going to be in terms of a third variable, more than likely t. And that third variable is what we call our parameter, hence the name parametric equation. So instead of like y equals x squared, we plug numbers in for x to get y coordinates. We're actually going to have two equations, x and y, describing each of the coordinates, okay? And we can plug values in for t to get our xy coordinates. Okay? So we're going to have two equations in terms of a third variable, and that third variable is called our parameter. Okay, so this is kind of what it looks like. This is what we're used to seeing as a rectangular equation, y and x, right? One equation. Here is what a parametric equation, a set of parametric equations would look like. X equals y equals, okay, in terms of a variable t. Now, t we associate with what word in math? T we associate with time, okay? And when we look at applications of parametric equations tomorrow, we are going to look at t equals time, okay? So if now today we might have some negative t's and that's okay, all right? But as t progresses, we get these coordinates, okay? So what happens with parametric equations is we're actually going to have an orientation. We're going to have these arrows describing the path of the curve, okay? So as t increases, our set of points goes in this direction. So we're going to have arrows describing that motion. Okay. Anytime you graph a set of parametric equations, you must indicate the orientation. Okay, and I'll show you how to do that. But without those arrows, it's not parametric. Okay, that's what's going to set apart a regular graph from a parametric graph. Okay, so let's try one. Okay, and I'm actually going to give you one where I'm giving you what I want the t values to be. So we have x equals t squared minus 4 and y equals t over 2, and I only want us to graph this between t is negative 2 and 3. So what we're actually going to do, instead of making an xy chart, we're going to make a txy chart. Okay, so we're going to plug values in for t to figure out our xy coordinates and then plot those. Okay, so this is giving us where we want the t values from. So we're going to begin when t is negative 2 and end when t is 3. So when t is negative 2, plug it in, what do we get for x? t is -2, we plug it in, what do we get for x? 0. And then if we plug it in for 1, -1. So we're beginning at 0, -1. Okay. Then we'll move to t equals -1. If we plug -1 in for t, -1 squared minus 4 is 3. And for y, -1 over 2. Okay. Then we'll move to t is 0. When we plug 0 in for t, 0 squared minus 4, and 0 over 2. Now we'll move to t equals 1, and we have to go all the way to 3, correct? Okay. Pods 1 and 2, plug in 1 for t. Pods 3 and 4, plug in 2 for t. Pods 5 and 6, plug in 3 for t. We'll do some teamwork here. When you have the coordinate, check with your neighbor. Pods 1 and 2, what do you get when you plug in t as 1? -3, +1/2. Okay. Everyone agree with what Josie said? Okay. Pods 3 and 4, when t is 2. Zero what? We're okay with 0, 1? Okay. 5 and 6, what do we get when t is 3? 5 3/2. We all good with that? 1, 2, 3, 4, 5. Okay. Now, we need to connect the dots and indicate orientation. Now, this is the coordinate when t was -2. And then this is the coordinate t is -1, 0, 1, 2, 3. Okay? So since we trace our coordinates in order by their t value, that would be our orientation. Okay? We started here and we ended here. So our arrows need to indicate that. Questions? Okay. All right, so now let's look at another graph. But this time I'm not giving you anything about what t needs to be. Okay. So we have x equals the square root of t and y equals t plus 2. Okay, so I have a question. If I look at x equals radical t, do we have any restrictions on what we can plug in for t? Why does it have to be positive? Okay, I have a question, Sean. Can we plug in 0? We can't take the square root of 0? Okay, can we take the square root of 0? Yes. Okay, what can we not do with 0? We can't divide by 0. The 0 is safe anywhere else, okay? We can't take the square root of 0. So, we cannot plug in values that are negative into the x. t has to be greater than or equal to 0 here. Can I plug anything into t for the y equation? We can. Here, okay, t can be anything, right? But since I have a restriction for x, we have to look at where these two are going to overlap. So our domain, okay, in this equation is when t is greater than or equal to 0. Okay, that's going to win over. Okay, so if we want to make a txy chart, we have to begin at 0 because we cannot plug in negative numbers. Okay, so when we plug in 0, square root of 0 is 0, and then we have 0 plus 2. Then we can try to plug in 1. Square root of 1 is 1 plus 2. Okay. Then we can plug in 2. We get square root of 2. 2 plus 2 is 4. That's not a really nice coordinate to plot. We can plug in 3. Square root of 3. 3 plus 2 is 5. That's not really pretty either. When we plug in 4, square root of 4 is 2. 4 plus 2 is 6. So we have the coordinate 2, 6. I'm going to plot that one. The other ones are there. I'm just not going to plot them for right now. What is this starting to look like?
Parabola.
It looks like a parabola, right? But is it the entire parabola, Tyler?
Yeah.
Okay. We're beginning at t is 0. And this parabola is going to go on for forever, only in the positive direction. But we don't have this other half of the parabola because we can't plug negative values in for t. Okay, so those are some important things to think about. Let's think about the times that we have domain restrictions. We have domain restrictions when we have a radical. Our radical can't be negative. We also have domain restrictions when else? When they give it to us. Okay, I mentioned something earlier about dividing. We can't divide by 0. So if we have some sort of fraction, okay, we don't want that denominator to be 0. So those are some things we have to think about if we're going to have any sort of restrictions on t. Okay, now we can plug values in for t and plot some points and get a shape. Okay, but do you think that there could be a more efficient way of coming up with a graph? Probably since I'm talking about it, maybe. Okay. So what we're going to do next is we're going to eliminate the parameter. What is the parameter in this set of parametric equations? Our parameter is t. Okay. So if we want to take a set of parametric equations and compare it to a rectangular equation, we can what we call eliminate the parameter. Okay. So essentially we're taking a set of parametric equations and writing it as one equation without the t. Okay, we're going to look at a rectangular equation. All right, so this is what we're going to do. We're going to solve for t and then substitute it in. Okay, we have two equations in terms of a third variable. We're going to pick one equation. It doesn't matter which one, whichever one is easiest to solve for t, and then plug it in. Okay. And then we'll want to simplify because this may be an easier way to come up with our graph. Okay, instead of plugging in numbers for t over and over and over and over, we can figure out what the rectangular equation is so that we can graph it and then put in the orientation. So we're going to go all the way back to the very first example that we did. Okay? We're going to go back to this one, and we're going to eliminate the parameter. Okay? What did the graph look like? If we were to graph it in its entirety, what does it look like? It looks like a parabola, right? Okay, so maybe that is the kind of equation we're going to get, right? Let's find out. Okay, so we need to decide which equation would be the easiest to solve for t. Y would definitely be easier because we don't have that square, all right? So if we're going to solve for t equals 2y. All right? Then what we get to do is we get to plug that in. So x equals t squared minus 4. Or x equals 4y squared minus 4. Okay. If we were going to put this into standard form so we knew how to graph it, we would add 4 and then divide by 4 so that now we're in standard form, right? Where's the vertex of this parabola? Negative 4, 0. And we know it's going to open to the right. Why do we know that? Coefficient's positive. Great. All right. You know, with 4p equaling 1/4, that might not be the most accurate way to plot this parabola, right? Plotting little points that are 1/16 away. All right. But you know, if you plug in some like if we plug in 0, we're going to get y squared is 1. So y is positive 1 or negative 1. We know we have a parabola. Okay. Now, from here, how do we know the orientation of our graph? How do we know where to put the arrows if we're using this kind of equation to graph it? How do we know? Any ideas? Okay, that's an idea. How will we know for certain that that would be the case? Is there any way to tell that, yes, it should go that way? I mean, I like where you're going with it being positive. Okay. Come back up to your parametric equations. Okay. Think about plugging in a couple of t values. If I plug in 0, we're at negative 4 1/2. If I plug in 1, we're at negative 3 1/2. So we know that, okay, here was t is 0, here is t is 1. We know it has to go this way. Okay. You're always going to have to revert back to plugging in a couple of t values, but it's not always efficient to plug in t values to get your entire graph. Okay, I want to take a step back to this graph for a moment, and I want to eliminate the parameter here. Okay, so I'm actually going to give you about 1.5 to 2 minutes to see what you can come up with for the rectangular equation here. I want you to eliminate the parameter on this one. Do we have somebody brave and willing to offer their answer? There's a couple different answers that are acceptable. Y equals x squared plus 2. How many of you got something like this or a version of it? Okay. Any other answers people had? So this is basically, Matthew, did you solve for t in the x equation and plug it in? Did anybody solve for t in the y equation and plug it in? Nathan, what'd you get? You got the same thing, so you went ahead and solved for y. Okay. Josie, did you? X squared equals 1. Okay. So it's the same version. Did anybody leave it as a radical? Okay. So let's talk about this. Some people went for the x and solved for t, plugged it in, so you would have had t equals x squared, plug it in. Some people said t equals y minus 2, plugged it in, squared both sides to get rid of the square root. Now, look at the graph that we drew and look at the equation. Do those two match? Some of us are saying yes, some of us are saying no. What is the issue with that graph and the equation? Why don't they 100% match up? It's not a full parabola. And why do we not have a full parabola? Because we have a restriction here, okay? If one of your parameters has a restriction, that means at the end, your rectangular equation might have a restriction, okay? So what would we have to write next to this? What is our restriction on the graph in terms of our x values? Okay, then that's what we need to write. X is greater than or equal to 0. You would have to write that with your rectangular equation because we have this domain restriction here. So since t is greater than or equal to 0 and x is radical t, then x is going to be greater than or equal to 0. Does that make sense? That we would need to add that on? Okay. Couple more examples here. Look at this one. What? If you, yes, I think that is a good thing to identify right away. If there are any restrictions, it'd be a good thing to point out. So, what was the restriction you just said? Okay, so you're saying t can't be 1. Michael, why did she say t can't be 1? Okay, we can't be dividing by 0. All right, great. Now, let's go ahead and eliminate the parameter and then think about the graph. Okay, so Maggie, if you were to choose one, which equation would you choose to solve for t? Choose x. Is everyone okay with her suggestion? I think this would be one of the cases where you really only have that choice. I don't think you want to try to solve for t in the second one. I think that's going to be a lot more work in the end. Okay? Always stick with the simpler of the two. All right? So x plus 1 equals t, which means when we go to plug it in, y equals x plus 1 over x plus 1 minus 1, or x. Okay, so now let's think about this. if we cannot plug in t is 1, and we know that x is t minus 1, what would that make the restriction here? X cannot equal 0. Now, why did that make sense for this equation? Okay, what's different about this equation compared to the parabola one is this one has that restriction in the end anyway. Why? Because x is in the denominator. Okay, so sometimes we get restrictions that are going to be there anyway. Sometimes we have restrictions that we have to write down and it's going to change our graph. Okay, so this might be some good review. How do we graph one of these things? What's happening at x equals 0? What? It is not a hole. There is an asymptote at x equals 0. Okay. We also have a horizontal asymptote. Does anybody remember where our horizontal asymptote would be in this graph? Why -1? If our numerator is 0, that means our fraction would be 0. And that would mean y is 0. And so we would actually have a coordinate there. So we actually have a coordinate at -1. What's true about the degree of the numerator compared to the degree of the denominator? Same, bigger, smaller? Same. And where is our horizontal asymptote when our degrees are the same? It is not at 0. We have a horizontal asymptote at 0 if the denominator has a bigger degree. Okay. So what do we look at? The coefficients. Our coefficients, 1 over 1, so y equals 1 is okay. Now, we've graphed these before. What is this curve going to look like? Trace it with your finger. We're going to have a little curve up here. We're going to have a little curve right here. Remember those? Okay. Ooh, but these are parametric. Those arrows don't go there. We have to figure out our orientation, right? How do we figure out our orientation? Okay, go back to the original. We know we cannot plug in t is 1. What happens when we plug in t is 2? We get 1, 2, which is there. And then if we plug in 3, we would get 2, 3/2. So that curve is going that way. Okay.
I think it's this like the bigger one and smaller.
Okay, say that again.
Like I don't understand how you understand that.
So like my first coordinate, when we plugged in 2, we were at the coordinate 1, 2, right? So 1, 2, and then when we plug in 3, we're at the coordinate 2, 3/2. So since we went from here to here, we know it has to go that way. And those can be calculations that if you want to make those coordinates, you can. If you want to think about it in your head, I would not guess. Yes.
On a graph like this, are both like pieces of the graph going to be going in the same direction? Or is it possible like one has to go in the opposite direction?
I suppose it could be possible that they could be going in opposite directions. So it may be safe for us to check. Okay. That's probably a good point. So we can't plug in 1. If we plug in 0, we're at -1, 0. And if we plug in -1, we'd be at -2 something. So it is indeed going that way. Because I plugged in backwards, right? This is t is -2, this is t is, excuse me, t is -1, this is t is 0. So we know it's going that way. Okay? All right, one more example where I'm going to make you think, and then you get some time to work on your homework. All right. Here is an example. We still have a parametric equation where our parameter is theta instead of t. Okay. But this is going to be slightly unique. Okay. Now we have x equals 3 cosine theta, y equals 4 sine theta. Okay, solving for theta to plug into the other one. How do you feel about that? Why did you say yeah? Okay, we'd have to do like some inverse cosine or some inverse sine and plug that into the other one. Okay, have we really done that before? Plugged in an inverse cosine to a sine. We really haven't. Let's not start now. Okay? Is there anything we know about a cosine and sine function? Any relation we have with the two? We have tangent. We know that tangent equals sine over cosine. Do we have any other relationships with sine and cosine?
We have those equations.
1 plus tangent squared is secant squared. So that doesn't have anything to do with sine or cosine. So keep going with that, but which one do you need to think of there?
Sine squared plus cosine squared equals 1.
Sine squared plus cosine squared equals 1. Okay, now Matt suggested the tangent of theta equals sine of theta over cosine of theta. I think that is really great, but the only problem with that is there's still that theta. Okay, now, Sean said cosine squared plus sine squared equals 1. Is it possible for us to solve for cosine theta? Leighton, what's cosine theta? Cosine theta is x over 3. And is it possible to solve for sine theta? We could write sine theta as what, Courtney? If we solved for sine theta, what would we do with 4? Yeah, so sine of theta would be y divided by 4. So now, instead of cosine theta, we could write what? X over 3. So instead of cosine squared, we have x over 3 squared. And instead of sine squared, we can write y over 4 squared. And what do we have? What is that? It's an ellipse. Crazy how all of these graphs from last chapter keep popping up. Okay? What kind of an ellipse do we have? Horizontal or vertical? Amanda, what kind?
Vertical.
Vertical, great. Maddie, what is our A value? 4. So we're going to go 1, 2, 3, 4. 1, 2, 3, 4. B value. What is it, Sarah? Or B value? Is 3. Okay, so we know that our ellipse looks like this. But what does our ellipse need? Arrows. So we need to decide, is this going clockwise or is it going counterclockwise? Okay, how could we make that decision? Okay, plug in points. Now, since this is defined by theta, I would plug in some nice radians. Okay, so let's think about plugging in 0. When we plug in 0, 3 times cosine of theta is 3. 4 sine of 0 would be 0. So here is theta is 0, right there. If we plug in pi over 2, 3 times pi over 2 is 0. 4 times sine pi over 2. So then, next we have this coordinate here. That will not always be the case, so don't just assume that it's counterclockwise all the time. You always want to test it. All right? So, the homework that you have for me is this. 7 to 27 odd. You need to eliminate the parameter and you need a graph. Now, I can't remember what order that they ask it, but don't worry about the order in which they ask it. Just give me a graph and eliminate the parameter. Which one you do first, it doesn't matter. I think sometimes it's easier to look at the rectangular equation and then think about the graph, because sometimes you can get a quicker graph that way. 61 to 65 odd. These are some problems where I'm going to give you an opportunity to be creative. I'm going to give you an equation, and I want you to come up with the parametric equations. Okay? So you're going to be a little bit creative. All right? But we have 8 minutes left in class, so you can maybe get a couple problems done before you leave.